Hello, my name is Jake Domingues, and this is my lab for constant velocity. So let's get right into it. First of all, this lab is a simple comparison between two models of motion that measure constant velocity over distance. So first coming into this, I hypothesized that our predictive model using a computer will differ slightly from the actual physical model due to factors that might impact the system. But this whole process is due thanks to Newton's second law of motion, or the momentum principle shown on the right, where total force equals the change of momentum over change in time, where momentum equals mass times velocity. So what's actually happening here? In the experimental model, I took a small ball, a pickleball, and rolled it across my dorm's AC unit and measured values using a video tracker system on Windows. My computational model used GlowScript. I just copied the same exact initial values from the video and made them go the exact same distance, but without any external forces. So this is the experimental model of the ball rolling across the AC unit. And this is what my video tracker software looked like. I used it to track the ball's X position, and it also calculated the velocity along the 1.35 meters. And this is what the computational model looked like. And this is all the code, but simply all you're going to need is the initial conditions, so including the ball mass, the initial position vector, as well as the initial velocity vector when it begins rolling, as well as the initial time vector in my video that was 1.8 seconds, as well as a delta t value, which will t cycle in the while loop over on the right for the ball position. The ball position will be updated based on the t cycle, which is also due to the frame rate, which is 60 frames per second. So every 0.033 seconds, um, this while loop will continue until the end of the ball's rolling, and will update that position 0.0165 meters, which equates to 0.5 meters per second, which is the initial vector. So these are the graphs. The red lines are going to be the experimental models that I found in the tracker system, and the blue lines are going to be the computational vector lines. As you can see, the red lines are not completely linear, and they do not match up perfectly with the computational model due to external forces that we'll see in a moment. But they do have the same trends, and they do line up pretty well. So what's actually going on here? First, we need to talk about system and surroundings. System is what's measured in an experiment. In this case, it's the ball in the computational and experimental model. And the surroundings on the bottom here are everything that's acting on the system. So the computational model has no real surroundings because I'd have to explicitly code that. But the experimental model does have many other objects that could be affecting the system, like a friction force or slight imperfections in the ball itself. So Newton's second law actually states that the total force in an object equals momentum divided by a recorded time period, like I said earlier. The momentum is equal to mass times velocity as well, and in this case, the initial velocities of both systems are equal, and therefore their initial momentums are also equal. But the existence of forces would also imply a change in the momentum of the ball in the experimental model. So this change of force changes momentum, changes velocity of the ball, which decreases as the time goes along, shown in the graph. So what if, when I analyze the video in Tracker, I flip the axes for graph and position and velocity? There are two main things that would happen if I flip the axes. If I flip the x position graph, so if I just multiplied them all by -1, then it would flip the direction. The slope would be negative, as you can see in the graph that I made on the right. Um, this is the same thing for velocity. It would completely flip that derivative because velocity is the derivative of position. So then it would set a constant line at -0.5. Same thing would happen if I flip the times. It would trend down with a slope of -0.5, and the velocity would not be negative though, because the velocity is still sitting at 0.5 no matter what the time is. So what does it mean that my observations are predicted well by the computational model, and I set the net force equal to 0 in that computational model, but is it possible for me to try and say how many forces or calculate how many forces are added together in the experimental model that we analyzed? But the forces described in this class and that I've been talking about so far are from point masses. So that's when all the mass of an object is located at one exact point. There's nothing like that in here. The ball is not a point mass. It's located in different points of space, and that makes up the physical ball itself. Interactions between the different spaces on the surface have their own different interactions on one another, and this is also they're all going to have their own separate interactions with the friction surface, the I don't know, imperfections of the surface itself, and that could all provide different force changes, and that's what gives us that slight difference in the graph. The fact that the ball is rolling is also proof that there's a friction force on the ball because it would just slide along the surface as there was no friction. So in short, no, I don't know a way how to calculate the number of individual forces on the observed ball at any given moment, but we do know that there is at least one. Thank you.